Okay, class, so this next lesson of our electricity unit is going to be on electrical power and efficiency. Okay, so just a little bit in regards to electrical energy before we get into electrical power. So far we've learned that electrical energy is like the energy of moving charged particles. So electrical power is the rate at which electrical energy is produced or used. So electrical power is what we need in order to, say, like power our homes. So the rate at which electrical energy is produced or used to power all the things that need to be powered. So, you know, the microwave and the dishwasher and the washing machine and the dryer, the toaster, etc. So the unit of measurement for electrical power is watts. Okay, so that's the unit of measurement for electrical power. So just like a unit of length would be centimeters, well, the unit of measurement for electrical power is specifically in watts. Okay, and 1 watt is also equal to 1 joule per second. The higher the wattage, the higher the energy usage. So some devices require more energy to be used than others. So a device that has a higher wattage is going to require more energy in order for it to be able to operate and work or perform its task. This measurement combines voltage and current. So we're going to get into this in a little bit more detail in the next couple lessons, but current, we're going to learn that that is the flow of electricity or the flow of electrons, and voltage is like the difference in amount of energy between two different points. So electrical power takes all of this into consideration. Okay, again, so power is the rate per unit time at which electricity or electrical energy is transferred. So I have an example here. It says 60 watt incandescent light bulb versus a 15 watt fluorescent light bulb. So this is an example where we have two light bulbs, both of them producing the same amount of light, but one having extra energy being given off as heat. So this is a great example of showing efficiency between different types of devices or appliances. So you could have an incandescent light bulb that requires a higher wattage, so 60 watts, versus a fluorescent that only requires 15 watts, but they're both producing the exact same amount of light. So that's going to make the fluorescent a lot more efficient than the incandescent. And the reason why the incandescent requires more wattage is because the energy that it's producing, a lot of that energy is actually just being given off as heat. So I don't know if you remember these incandescent light bulbs, but they're the ones that get really, really hot. So you can't touch them because all of that energy is being given off as heat. So that's like a waste of energy, because a light bulb, what do we want it to do? We want it to produce light, not necessarily heat. So this is a good example of one producing heat energy and one producing only light energy, making it more efficient. If both products are producing the same amount of light, you're going to want to choose the one that requires less power. Okay, so measuring electrical energy usage. So there's something called electricity meters. Electricity meters keep track of how much electrical energy is used in homes, schools, and businesses in units of kilowatt hours. So kilowatt hour is the unit for measuring electrical energy usage. So use of 1 kilowatt of power for 1 hour. The average Canadian family consumes 16,000 kilowatt hours. So I'm sure many of you guys have seen these electricity meters outside your homes, or are connected or attached to your homes. So these right here and here, these actually measure how much energy or how much electrical energy in kilowatt hours that home is using. So you can't see on this diagram, but if you were to zoom in, you will see that the units on the electricity meter is in kilowatt hours. So it's kind of like something that monitors and records how much electricity is being used in the home. Okay, energy efficiency. It says here, efficiency, comparison of energy output with the energy supplied. So it's important to choose appliances or devices that are very energy efficient, okay? And the actual definition of energy efficiency is comparing the energy output with the energy actually supplied. So really that's saying how much energy is actually like contributing to powering the device versus what's being supplied in order to just kind of turn it on. So for example, one old clothes dryer might require 800 kilowatt hours in 1 year, whereas a new clothes dryer might require 300 kilowatt hours in a year. Both perform the same task, but one requires 60% less energy. So this is a comparison of efficiency. The old clothes dryer needs a lot more energy supplied versus how much it actually puts out, whereas the new clothes dryer, however much it needs or requires just to work, is going to be approximately the same amount that it puts out to perform the task. Okay, so the new clothes dryer is going to be more efficient. It's not going to have much waste energy, whereas the old clothes dryer is less efficient and it's going to have more waste energy. Another example here is a 100-watt incandescent light bulb uses 40 kilowatt hours and 400 hours versus a 25-watt compact fluorescent light bulb or lamp only uses 10 kilowatt hours and 400 hours. So again, this is another comparison where the CFL only requires 25 watts, whereas the incandescent requires much more, 100. Okay, and in the same amount of time, 400 hours, one is using less kilowatts per hour. So the CFL is only using 10 kilowatts per hour, whereas the incandescent is using 40 kilowatts per hour. So again, just a comparison of efficiency. Compact fluorescent lights contain small amounts of mercury, so it's important that we dispose and recycle them properly. That's very important. In an LED, the light emitting diodes, that is one of the most efficient types of light bulbs. Okay, so efficiency again is like how much energy is required versus how much energy is put out to actually do the task. Okay, so this is just a table here, guys, just showing electricity use by households, like with different lighting and appliances. So you'll see in the first column it says average electricity use per unit. So we have refrigerator, television, dryer. Okay, that's giving you how much electricity use in kilowatt hours per year. And then we have in the second column the average number of these per household. So the average number of TVs is 2. And then the average electricity use per household in kilowatt hours per year. Okay, total. So this would be the total. So it's just to kind of give you an idea as to how much energy is required to use these different appliances. Okay, so the EnerGuide and Energy Star labels, some of you have probably seen this before. So when you're buying different appliances like a dishwasher or a washing machine or a dryer, it's very important to consider the price, but it's also much more important to consider the cost to operate that appliance or device. So it's very important to look for the EnerGuide. So if you guys look right here, this 81 is giving the energy efficiency rating. So again, it's important to keep into consideration that maybe something might be cheaper to buy up upfront, but it might be much more expensive and inefficient to run or power over the years. So it's good to look for this energy efficiency rating. If you're over in this area here, okay, that's a low efficiency. So this 65 to 100. Okay, so this is kind of like a scale or a rating system to provide, it's like a calculation of how efficient that appliance or device is. So look for EnerGuide, how much energy the product will use in a year in kilowatt hours. The Energy Star label identifies products that meet a minimum level of efficiency. So you're always going to want to choose products that have these Energy Star labels because they are meeting the minimum requirements of efficiency. Okay, so now we're going to learn a couple different calculations. So calculating efficiency. You're going to come across some word problems where you're going to calculate how efficient is this product, appliance, or device actually. So we have an equation here. Percent efficiency is equal to energy out divided by, remember that line there, guys, is a divided by energy in, and then times 100%. So percent efficiency equals E out for short form divided by E in times 100%. So remember, when reading through these word problems, energy out is the measure of how much useful energy the device puts out to do its tasks, whereas energy in is the measure of how much energy the device requires. So energy in is how much it needs no matter what in order to just work, whereas energy out is kind of like how much energy it actually produces in order to fulfill its tasks. Okay, so let's give this sample problem a shot. So it says here, a light bulb uses 100 joules of electrical energy and produces 25 joules of light. Calculate the percent efficiency of the light bulb. So number one, if we're calculating percent efficiency, we're going to use the equation that you see on the video here. So percent efficiency equals energy out divided by energy in times 100%. Now the hardest part is just differentiating or deciphering between which is energy out, which number, and which is energy in. So remember, energy out is the useful energy put out to do the task. So if it's a light bulb, that means that there needs to be some sort of energy transformation here. So energy in order to just make it work, would be electrical energy, and then energy out, the type of energy that a light bulb is producing, in the end would be light energy. So that's one way to differentiate between the two. Another way is when it says, for me at least, produces, that always helps me to determine that when it says produces, that is the energy out. That's how much it's producing in the end. So it requires 100 joules of electrical energy in order to produce in the end 25 joules of light. So we're going to start off by writing down what we have. Energy out is how much it produces, or how much it puts out to do the task. So that's going to be 25 joules, and energy in is going to be how much it requires. So that was the 100 joules of electrical energy. So now we're going to use our formula here. So trying to be as neat as possible. Percent efficiency is equal to E out. So we know now that that is 25 joules divided by E in, which is 100 joules, times 100%. So we can do the 25 divided by 100 first. Okay, that's the first step, the division. So that's going to give us 0.25. And then now we're going to times by 100%. That gives us 25%. Okay, so we have calculated the percent efficiency of this light bulb. The percent efficiency is 25%, and I want this to make sense to you and put into perspective like real world application. 25% efficient is not efficient at all, right? Something that's very efficient is going to be 100% efficiency. So the further away from 100%, the less efficient it's going to be. So this light bulb is only 25% efficient. So now I just want to do one extra step where we calculate the waste energy. So we know 100% efficient is 100. So if we subtract the 25% efficiency of this light bulb, we get 75% waste. So that means that in order for this light bulb to work, okay, when we compare how much in versus how much out, 75% of the energy is being wasted, okay, and it's only 25% efficient. So low efficiency here. Okay, next, time use of electrical energy. So it says here, price changes throughout the day. Most expensive time is during the weekday from 9 to 5 p.m. So this is like peak times. So I'm sure you guys have heard of this before. There are certain times of the day, maybe mom or dad asks you not to do laundry or not to run the dishwasher during a certain time of the day because those are peak times. And during peak times, it's most expensive to use this electrical energy. Use energy outside peak times because this saves money and reduces pollution. So there's something called smart meters. So these are the electrical meters that are connected to your home. Again, they measure the amount of electrical energy that's being used, and they also measure how much time it's being used for. Okay, so again, this calculates that kilowatt hours, how much energy is being used and for how long and at what time. Okay, so we're going to learn a second equation here, and it's to calculate the cost of electricity. So the equation here is cost to operate, and this involves the power used. So always the units when using this formula for power need to be in kilowatts, times time in hours, times cost of electricity in cents. Okay, so this is the equation. Those are our units, kilowatts, hours, and cents. So let's look at this example here. It says a laptop computer uses a 7.5 watt adapter when it is plugged in. Electricity costs 5.6 cents per kilowatt hour. Calculate how much it would cost to operate the laptop for 1 year for 24 hours a day. So these ones can be a little bit more difficult. There's a lot of information, but we're just going to pick out all of the information we have, and we're going to sub it into the equation. So number one, the question asks, calculate how much it costs to operate. So we know right there that we're trying to determine cost to operate. Okay, that means that we must have power use time and cost of electricity. So let's write down what we have. So it says 7.5 watts. Well, we need to be very careful. Sometimes the question will give you in kilowatts, but in this case, power, okay, power has been given to us in watts. That means that we need to convert 7.5 watts into kilowatts. So that's the first thing we'll do. So I'm going to put power over here. Okay, 7.5 watts. Now there are 1,000 watts in 1 kilowatt. So in order to convert watts to kilowatts, you have to divide by 1,000. Okay, so we're going to divide by 1,000 to get our answer in kilowatts. If you take 7.5 and divide by 1,000, we'll get 0.0075 kilowatts. Okay, so sometimes you have to do that conversion. If the question gave you power in kilowatts, then you're good to go, but in this case it was watts, so we had to convert. Okay, so next, let's write our time out. So this is a little bit tricky. Time, remember, is hours, okay? The question says, how much would it cost to operate the laptop for 1 year for 24 hours a day? So we know for 1 day, it's 24 hours, but this is going on for an entire year. We know that there are 365 days in a year, so that's 24 hours for every day for 365 days. So we have an extra calculation to do here. We have to do 24 hours a day times 365 days. we get 8,760 hours. And lastly, we need to put the cost of electricity. So cost, and the question gives that to us 5.6 cents per kilowatt hour. Okay, so keep in mind this is in cents. So sometimes in the end, we'll have to do a conversion to dollars. Okay, so now we have this information and we're just going to sub into our formula. So cost to operate equals power, which is 0.075 kilowatts. Oh, 0.0. Sorry, guys. That was 0.075 kilowatts times hours, which is 8,760 hours, times cost, which is 5.6 cents per kilowatt hour. Okay, so you're going to plug that all into your calculator. 0.0075 times 8,760 times 5.6, and you would get 367.92 cents. Okay, remember this is cost to operate, so if you need to cross off all the doubles, kilowatts, hours, kilowatt hours, we have two of those, we're left with cents. Okay, so we don't talk money, we don't say 362 cents. We only say cents if it's less than $1, right? So we're going to convert this cents into dollars. So we know that there are 100 cents in $1. So in order to put this into dollars, we're going to divide by 100. Okay, so divide by 100. We are going to get $3.67, or if you're rounding up, okay, this 9 is going to make the 7 an 8, so $3.68. Okay, so that's a question that involves a little bit more steps. Okay, but just write down what you have, plug into the formula, and then convert to dollars if necessary. Okay. Cost of electricity. So operating one device for a year is fairly inexpensive, but we need to remember we use many devices and they use energy even when they are in standby mode. So guys, even something that's plugged in is going to use a little bit of energy. Also costs for distribution or transmission of energy. Okay, so you guys have a little bit of practice on pages 18 to 19 in your booklet. So this involves using the cost to operate equation and the percent efficiency equation. Thanks, guys.